years, and the driver will give the feedback about the car. Based on the feedback, there will be some modifications happen in it. Then finally, you will come up with the final product that will reach the market. So these are all the different types of prototype. But the problem in making prototype is it is very complex. Making component for very few numbers is very difficult. Something if goes wrong, again you have to make the prototype once again. And prototype initially was done manually. It's a complex, tedious, and of course it's an expensive process that often delay the developmental time. So initially, before 1980s, you may see, for example, if you consider a car like an ambassador car, you cannot see many variants. You can see only one variant, and even that one variant exists in the market more than 10 years, more than 15 years, right? The reason is there is no rapid prototypings are available at that time. The product development time is very high, right? But now you consider, if you consider a Swift car, in the Swift car itself, you have different variants. Immediately after 2-3 years, they will come up with some facelift. Immediately after 2-3 years, they will come up with some additional new features. So the product development time gets reduced drastically because of the use of prototyping machines, rapid prototyping machines. So you are making prototype in a very fast way. So you can call the prototyping machine as a rapid prototyping machine. As I mentioned already, these machines are only meant for making prototype in initial days, maybe from 1990s to 2010. After 2010, people understood the capabilities of that machine. So these machine not only used for making prototypes, these machine has the capability to make final parts that can be directly used into the assembly, that can be directly used into the product. Then you should not call that machine as a prototyping machine. You should call that machine as some manufacturing machine. The main principle behind in making this prototype was you are adding material layer by layer in order to get the final product. So people called this machine as additive manufacturing machine instead of rapid prototyping machines. I hope you understand why the name stands as additive manufacturing instead of a rapid prototyping machine. And you all know why prototyping is required actually. First of all, to get a clear communication between the producer and the customer. Sometimes producer may talks about a cat, for example, but the customer may thinks about a tiger, right? So in order to eliminate this bad communication, you need some prototype to get a better clarity. So for that, these machines are very useful. And to decrease costly mistakes, sometimes people will make the final product without making prototype. And after, when you enter into the market, immediately the customer comes up with the feedback. This is missing, that is missing. Then what you have to do, you have to change all the dies, you have to change the production, you have to change all your product planning. So everything gets collapsed. Finally, the product will fail. So this leads to a failure of product. So that can be avoided if you make a prototype first. And it extends the product development lifetime by adding necessary features and sometimes to eliminate the redundant features in the design stage or prototype stage itself. And finally, to have a number of variants in the product, because nowadays customers are customers asking customized products for their purpose. So they look for different variants, they look for different features. Everyone has some unique idea, unique what do you call unique things they require. So in that case, if you come up with a common product, they won't like normally, right? So if you want a customized product, then you have to reduce the product development time. You have to increase the number of product variants. That and all possible if you use rapid prototyping machine. And of course, once the product development time reduced, the delivery time also decreased drastically. So this is the need of going for a rapid prototyping machine. And as I said early, this rapid prototyping term is used in the beginning of the professional use of the technology, because the main application is manufacturing prototypes, markups, and sample parts. But now the trend is completely changed. The machine is having the capability of making final part that can be used in the product. So the ASTM committee has recommended the name for the rapid prototyping machine as additive manufacturing machine, or simply you can call it as additive manufacturing. So as said already, the basic principle of this technology is that a model is initially generated using a 3D computer aided design, right? So the prerequisite for making your part is a 3D CAD data. The CAD data can be get from any of the design software, maybe a SolidWorks or Pro-E or Unigraphics or CATIA or Solid Edge or Autodesk Inventor. So any of the software. And if you feed that CAD data to the machine, so you have to do some pre-processing that I will explain you in the later stage. If you feed this data, it will fabricate the part without the need of process planning. So you all heard about the term called process planning, because in other manufacturing process, you need a careful and detailed analysis of the part geometry to determine things like the order in which the different features can be fabricated, what tools are required, what fixers are required, what are all the jigs are required, what are all the machines are required, and in which order. These are all the things you have to carefully plan. Then only you can make a part as per the given drawing. But actually, this is a separate department available in all manufacturing sector that is actually missing in the additive manufacturing. You don't want at all the process planning. All the features can be fabricated in a single machine itself. So it reduces the cost, because you don't have a separate department. You don't want to spend process planning time, right? So obviously what happened, the cost for making a part also gets reduced. It's a big advantage for a company, right? And the additive parts are made by adding materials in layers. Each layer is a thin cross section of the part which is derived from the original CAD data, right? So for example, this pyramid is your 3D CAD data. And by using some pre-processing software, you have to slice into number of layers. As I mentioned, each layer is a thin cross section of the part. You have to feed this sliced data in G-code form to your 3D printing machine. Then the 3D printing machine, what it will do is, it will print the thin cross section layer by layer. One layer it will print it. After that, the printing head moves upward for a given slicing thickness. Then it will print the second layer on the first layer. Then it will move ahead. Then it will print the third layer on the second layer. So like that, it will print layer by layer in order to achieve the final physical object. Additive manufacturing is a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing, such as traditional machining. As you know, in the subtractive manufacturing, what normally people will do, they remove the material, right? So this picture will give you a clarity about the difference between additive and subtractive. Most of you know about this, but just a recap. In the additive and subtractive manufacturing, conventional machining, you have to give the feedstock material in raw form. It may be prismatic or cylindrical. Then you have to feed this raw material to the machine. What the machine will do is, based on the drawing which is given to the turner or the machine operator, he will remove the material, unwanted material, right? If you remove the material from the raw material which you feed to the machine, you will get the final shape. This is your final shape. At the meantime, as a byproduct, you will get a lot of wastage of raw material. You can reuse it, of course, but this is again an additional process required to make this waste into the raw material once again. Whereas if you consider the additive manufacturing, initially the raw material will be in powder form, sometimes in wire form, sometimes as a thin sheets, right? But here what you do is to make the final product, you are adding layer by layer, right? You are adding layer by layer. So you will get the 3D final object from the machine. At the meantime, the byproduct, that is you called as a waste, will be very, very minimum. Sometimes it is negligible when compared to the subtractive manufacturing, right? So this is the greatest advantage for going for additive manufacturing, right? So when we talk about the process flow, there are different types of additive manufacturing technology, right? Not only powder fed additive, wire arc additive. We have a number of technologies available like stereolithography, selective laser sintering, what do you call sheet metal uh, fabric, you called as laminated object manufacturing, right? So there are different techniques that are available in the market, right? Irrespective of the technique, irrespective of the technology, the process flow or the steps involved in from CAD to your final product, it remains same. So this is the generic process flow of additive manufacturing. The very first step is CAD model generation. In the CAD model generation, it is done by a design engineer by using any of the design software. The second step is STL conversion. STL means standard tessellated language. Sometimes people will call standard triangulation language. It means that the surface of the CAD model are converted into small triangular facets. This is for the purpose of finding out the coordinates of each point, each surface point of your CAD, right? So once you find out, once you convert into a STL file formation, you have to feed the STL file to the pre-processing software. But don't think that the STL conversion is a tedious process. This can be done in the CAD file itself, the CAD software itself. In the CAD software, while saving your CAD file, your image, there is a drop-down list. For example, if you are doing a design in SolidWorks, defaultly the SolidWorks saves your part file in .sldprt. SolidWorks part file it will save. You can change the format. If you want, you can save it in STL file formation itself, or you can save it in IGES. So there are different file formats are available in the CAD software itself. So you can do it in that itself, right? So once you convert into your CAD file into an STL file format, you can feed that STL file to your slicing software. You call that as a pre-processing software. There are different types of pre-processing softwares are available. Most predominantly used pre-processing or slicing software is Cura, which is given by the company called Ultimaker. So it's a Cura software. So the purpose of this pre-processing software is once you feed the STL file, you have to feed the layer thickness. As I mentioned already, in the additive manufacturing, the product is made layer by layer. So you have to feed the each layer thickness. Say for example, the layer thickness is 0.4 mm. If you feed, or say for example 0.5 mm, you want to make a 10 mm size component, 10 mm height component. Then what it will do, if you give slice thickness as 0.5, then for 1 mm you need 2 layers, for 10 mm you need 20 layers, right? So it will slice into 20 layers. Each layer you have the different cross section or maybe sometimes same cross section. So for each cross section of a single layer, the G codes will be generated in the slicing software itself for each layer. So 20 layers, you have 20 layers of G codes. That G codes you have to feed to the machine. So you have to transfer the file to the machine. And in the machine also you can set some parameters. Like you can set the bed temperature, you can set the scanning speed, you can set the material which you want to print. So like the different parameters are there. It is depends upon which technology you are using, right? So once you set up the parameters in a machine, the next thing is you have to press the build button which is available in your machine. For initially for 2-3 layers, some supervision is required. Once the first 2-3 layers are properly laid on a build platform, then you don't want any supervision. Rest of the thing will take care by the machine itself. It will do print. Finally, the final product which will come out from the machine. You have to remove the final product from your build platform of the machine. And you have to do some post processing if required. Sometimes there will be some support materials you called a scaffold that you have to remove. Sometimes you do painting, sometimes you do some finishing operations, sometimes you will do some coating. So this and all comes under post processing category. Once the post processing is over, you right. So hope you understand the queries from the chat box also. So I'm just moving to the next slide. Next slide is about the classification of additive manufacturing. Before that, I can say some interesting examples why additive manufacturing is famous or fascinating in the field, right? So, for example, as I mentioned already, there are huge amount of waste which is comes out in the subtractive manufacturing, whereas in additive, wastage is minimum. You just think in the jewelry making industry, if you go for a jewelry shop, if you ask to give you a chain or some other gold ornaments, they will charge you a wastage charge. They charge you in three different components. One is the gold material cost, second one is making charge, third one is the wastage charge. Material charge you cannot avoid, you have to pay it. Manufacturing, yes, of course, there are some machines involved in it for making the desired shape, so you have to pay for it. But you just imagine wastage. Anyway, they are going to reuse it. They will reuse the gold, remelt it, they will use it further. Then why they are charging on you? Because while doing some subtractive removal of the process, the gold ore gets wasted. They are charging for 20%, 30%, right? You know that. So it depends upon the model they are charging. If the model is complicated one, they are charging up to 30 to 35%. You just imagine. So it adds cost to the ornament. You just think if it is made up of a gold 3D printing, the wastage will be very, very minimum. Then maybe they may charge you 1 or 2%. 30%, you just compare, is drastically reduced to 1 or 2%. You just imagine. But as of now, gold 3D printing is in the research level. Some of the Europe companies, they started using it, but in India, no one is using additive manufacturing for making gold ornaments. In maybe 5 years down the time, maybe some people will come with gold 3D printing for sure. And another important thing is complexity for free. When you talk about additive manufacturing, any complex profile that can be fabricated in a single machine itself. For example, if you make the same complex component by using some conventional machine, sometimes 3-axis CNC machine is not viable or not usable for making complex shapes. Then what you have to do? You have to go for a 5-axis machine. Obviously, what will happen? The manufacturing cost gets increased because 3-axis per hour rate may be 200 rupees per machine. Whereas if you go with the 5-axis, the per hour rate is 400 rupees. So obviously the cost of the component gets increased. Whereas if you use additive, either whether it is simple shape or a complex shape, you are using the same machine. So you don't want to add cost on it. So cost remains same. Simple or complex, cost remains same. Right? So that's why I called or coined a name complexity for free. Any complex without adding cost, you can make it. So complexity for free. And the second one is mass customization is possible. Right? You all heard about the term called mass production. Similar component can be produced in a mass number, thousands, 10,000, lakhs of component. For example, fasteners, for example, bearings, for example, washers. These are all manufactured in thousands and thousands of components. All are same dimension, all are having same feature. But you just think you want a components thousand, but each component are identical. Each component have unique feature which are different from the others. Right? If that is the case, you cannot depend on the conventional way of manufacturing. Yes, because conventional way of manufacturing is applicable for mass production. If you want mass customization, then you have to go with additive manufacturing technique. Right? So these two are the unique capabilities: complexity for free, mass customization. These two are the unique feature of additive manufacturing. Right. Let's go to the classification of additive manufacturing. As said, ASTM has classified the additive manufacturing into 7 broad categories. Start with VAT photopolymerization. You call it as stereolithography. This is the first additive manufacturing technique which comes into the market in 1988. Right? The second method is powder bed fusion, where the raw material will be in powder form, whereas in the VAT photopolymerization, the raw material will be in the liquid form. The third one is called material jetting, where the raw material will be in the wire form most of the time. Right? So and the next one is binder jetting. The raw material will be in the liquid, semi-liquid state, powder form. And the fifth one is directed energy deposition, where the raw material will be in the powder or in the wire form. And the next one will be the material extrusion, where the powder will be in the wire form. Finally, the last technique is called sheet thin sheets form. Right? So these 7 are the broad categories of additive manufacturing process. Among these 7, the very famous method everyone knows and every institute has, the material extrusion type 3D printers that we called as FDM, fused deposition modeling 3D printers, which you get this type of additive
7500 ആകെ ഒരു സെമ്മിന് ഫീ.
Am I audible, Umanat sir?
Yes, yes. Now you are audible.
ആലോചിച്ചിട്ട് തീരുമാനിച്ചാൽ മതി. ആയിക്കോട്ടെ, കുഴപ്പമില്ല. അപ്പൊ അത് ക്യാഷ് ഞാൻ
Umanat sir, is my screen is visible?
Yeah. Now it is visible.
Can you tell me where has I have to start from the classification?
Yeah, you just 1 minute only you exited. From this slide only you can start.
അഡ്മിഷന്റെ ക്രൈറ്റീരിയ.
Hello. You are on this slide only.
Now I entered. Yes. I will start. Yeah. Sorry, participants, because of some network issue in my place, it's getting disconnected. Sorry for it. So I am just sharing my screen and start from the classification. So as I mentioned, though there are different technology, today my focus is especially on the directed energy deposition, right? So before getting into it, because DED, directed energy deposition, shortly I called as DED, that belongs to metal additive manufacturing, right? So I just give you an introduction about metal additive, then we will get into the directed energy deposition, right? So metal additive manufacturing is a process of making a three-dimensional metal-based solid object of nearly any shape or design from the computer-generated framework, right? So it is nothing but making a metal component. We call that as metal additive manufacturing. Normally, the feedstock material, the raw material will be in the powder form most of the time. Sometimes you can use wire form also. And power source which is used in the metal additive machine is for melting the laser. Is the first one is design freedom. That is any complex profile, right? So irrespective of that, design, you can fabricate it by using metal additive machine, right? You don't want to think about design for manufacturability, right? So any complex profile can be built, so you have a more design freedom. Second one, reduced material wastage. As said already, you are adding material to get the final shape, so material wastage will be very minimal. Third one,
Prabhakaran sir, the screen sharing is stopped, I guess. You have to restart the screen sharing.
yes. Thank you. And the third one is faster time to the market. Because if you go with the conventional way of making a metal component, first thing is you have to make a die or you have to make a cavity to make the part. Then you have to do a process planning. Then you have to do machining and finally assembly. So it takes longer lead time to make a product. Whereas if you go with the metal additive manufacturing, you don't want to die, you don't want to zig, you don't want to process planning at all. So sometimes assembly, number of parts involved in a product also can be reduced. So that will make your product to what do you call it as stock your jigs, fixtures and other items, right? So directly you feed the material and finally you will come up with the final product. So just-in-time manufacturing is implemented in additive manufacturing. Material flexibility. So not like conventional soft materials are not possible, very hard material. If the material is having is possible. So customized for the users are possible if you use metal additive manufacturing, right? So these are all the pros of going for metal additive manufacturing. In the metal additive manufacturing, commonly we can broad category, and these three broad categories of metal additive manufacturing techniques are available, but still these three are widely used by the customers. Start with powder bed additive manufacturing, that you called as selective laser melting, that you know are learned already. And the third one is wire arc additive manufacturing. I am going to cover these two topics today, right? So these powder fed and wire arc additive manufacturing comes under the family of directed energy deposition method, right? So I hope you remember the 7 classifications of additive manufacturing. These two techniques that and all comes under the umbrella of directed energy deposition, right? So So in the laser DED system, there are three main components. One is a laser beam that provide a thermal energy to melt a metal powder or metal raw material. Second one is a feedstock delivery system that blows powder or inject wire into the melt. And finally, the third important component is a motion system that translates the laser beam and feedstock relative to the substrate, right? So this is actually the laser head. At the center, you have a laser beam. On the other two sides, you have a powder feed. The tandal coincide at one point and it is interact with the substrate. On the substrate, the solidified metal powders are laid on the substrate. The substrate may be a base plate or the substrate may be the existing product also. So this technique is mainly used in repairing places. For example, you have a huge size gear. In a gear, one tooth is getting broken, right? One tooth is broken. So you want to replace or you can repair the existing gear. The gear cost is very high, so you can do what you can do is you can repair the existing gear by providing a gear tooth on the existing gear. So that is possible by the DED machines. So the DED uses a high energy density heat source as a laser that is focused on the substrate, forming a small melt pool and simultaneously melting the feedstock material also delivered into the melt pool, right? I hope you understand. So it will heat the substrate may be the base plate or maybe the existing part. Meantime, simultaneously, it will melt the feedstock material also. Most of the time, feedstock will be powder. Sometimes it will be wire. If it is wire and the heat source is electric arc, then you call that system as wire arc additive manufacturing. Hope you understand. So I'll repeat: if the heat source is electric arc and the raw material or the feedstock material is in wire form, then you call that technique as wire arc additive manufacturing. That we will discuss in the upcoming slide. Now we are discussing the laser DED machine or powder fed additive machine. In this machine, the heat source is laser and the feedstock material is powder. So laser powder fed additive machine or laser DED machine. So these are all some different names they coin, right? So here the working principle is as the heating source moves forward. So this is your heating source. See, here I have shown a schematic diagram of a laser DED machine which is held in a robotic manipulator. See, this is your laser head. Sometimes people will call it as a cladding head. This head is attached to the 6-axis robo or any of the motion system, maybe a normal CNC 3-axis machine. So wherever the robo or CNC system moves, accordingly your laser head moves. In the laser head, you have a laser at the center. On the annular, you have the powder which comes into the laser, right? And the laser simultaneously melt your base plate, meantime your feedstock material, then the molten feedstock material laid on the build platform layer by layer. So this is actually the one layer, and this you called as the deposited layer. Over that, the second layer will be deposited. Over that, the third layer will be deposited. Like that, it will be deposited layer by layer. Finally, you will come up with the final three-dimensional component. And as mentioned, the heating source moves forward. The deposited metal solidifies on the substrate, forming the metal track. This you called as metal track. The metal track overlap each other based on the predefined hatch spacing. So once one layer is completed, the deposition head, or you called as a laser head, and the feedstock delivery system move upward by a small distance. This is based on the slicing thickness you gave, right? So the deposition of all layers produce the 3D near net shape component, similar to the CAD model. Before deposition, the 3D digital model is sliced using the software to specify slicing thickness, at spacing, and deposition path in each layer, right? So the unique capabilities of the DED machine is any metal that can be welded can be printed with DED. So any metal, right? Non-vertical material deposition also possible. You can use some positioner. So using that positioner, you can print non-vertical material deposition also. So complex profile can be printed by using the DED machine. Third one is build substrate can be empty flat plate or the existing part, onto which the additional geometry will be added. Third one, it can create complex shapes. Fourth one, adding feature to the simple shape is possible. Fifth one, site specific deposition and repair is possible. And finally, aluminum alloys, cobalt based alloys, nickel based alloys, stainless steels, titanium alloys, super alloys like Inconel, Hastelloys are possible to print in a laser DED machine. So in the powder feeding system, right, the powder feeding unit has different variants. The very first one is lateral feed. The powder will be fed laterally. At the center, you will have a laser. So you have some angular misalignment that you called as lateral feed powder feeding system. Second one is continuous coaxial system. At the center, you have a laser. Along the annular area, the powder will be fed. So this is the most predominantly used powder feeding system. Even the machine which is available in our PSG also having this powder feeding system. Third one is discrete coaxial, where at the center laser will be there, and along the annular area, discretely the powder will be passed towards the substrate. Fourth one is center feed. So at the center, the powder will be feeded, and the annular area, the laser will be passed. And the last one is at the center, again, the powder will be feeded, and the annular area, discrete lasers are placed, and it will melt the substrate simultaneously with the feedstock material, right? So maybe this video will help you to understand how the metals are melted. See, first the substrate will be melted by using the laser. Then only you will have an interaction on the feedstock material. Feedstock material also melted, and it is deposited on the substrate. Right, just moving to the next slide. The next system which is available in the DED machine is laser DED machine is an inert gas system, because in order to avoid the contamination or scale formation, you have to maintain an inert environment. Then only the melting will happen in a controlled atmosphere, so you can avoid scatter, you can avoid scale formation, right? So the process will happen inside the chamber. The chamber we call as inert gas supply system or a glove box unit. So the inert gas, which helps in two ways. One is to carry the feedstock material in the powder form. Normally, to powder will be carried by a inert gas towards your cladding head, towards your substrate, and the total the environment is purged. The total environment is maintained in an inert atmosphere. So for that also you have to continuously feed the gas, inert gas. Most of the time argon is used as an inert gas. Very few times or very few places helium or nitrogen can be used, right? So the parameters which is used or which is predominantly control the output of the product is laser power, scan speed, powder feed rate, laser beam diameter, build orientation, layer thickness, and hatching pitch. So these parameters, 7 parameters, are the predominant factors that affects the quality of the printed part, right? I just go into the application part of the laser BED. It is used in aerospace. It is used in automotive parts. It is used in medical industry, military and defense in sectors, repair and maintenance area, tooling, and marine industry. So these are all some of the pictures which is made by using the DED machine. Turbine blades, nozzle units, right? These are all some of the rocket components which is made by using the DED machines. So this is the machine which is available in our campus, which is indigenously developed by our team. This is funded by Department of Science and Technology. So which is the only one machine available in India having a build volume of around 1000 mm cross 1000 mm cross 1000 mm. So most of the DED machines are available in the market having the work volume of less than 1 feet cube, whereas this machine has the capability to build 1 meter cube component, right? So here for the motion purpose, for providing the motion, we use robot. We use an ABB robo. At the end of the rest arm of ABB robo, we have attached the cladding head. You can able to see. So this is your cladding head, which is attached to the end of your wrist arm of the robo. In the cladding head, you have a laser unit, and also the powder will be carried away by using a carrier gas, and it will be sent to the nozzle. And you have a laser power source. We use a 3 kilowatt diode laser. So any metal, even having the high melting point, can be easily melted by using our laser power source, right? So even for titanium alloys, which is having a high melting temperature around 1800, that can be melted very easily by using our laser power source. And we have a twin hopper powder feeder system. So you can feed, you can pour stainless steel powder here, you can pour some other powder here also, that can be blended and even that can be printed by using this machine, right? So the powder feeder unit will feed the powder from 2 gram to 20 gram per minute, right? So the powder which you supposed to use in this machine is any of the powder like aluminum alloy, stainless steel, titanium, super alloys, but the powder size should be less than 80 micron and about 20 micron, 20 to 30 micron, right? So normally which is available in the market, which is having a size of 40 to 80 micron. So that standard powders can be used in this machine. So this is the specification of our developed machine. I have mentioned the build volume here as 300 cross 300 because we are doing now some trials and testing is ongoing. So we are not building a higher size component. Less than 300 is possible as of now. And the power source which we use as diode laser, and the motion system We have a 6-axis robo along with 2 degrees of freedom. Positioners are available. So 8-axis system we have. So any complex profile can be easily built by using our machine. And material is mostly a metal powder, but that should be a non-reflective. That should absorb the laser, then only the metal gets melted. And the power laser powered is a 3 kilowatt laser. Laser spot size range is 0.85 to 3.3 mm is possible. Powder particle size is 45 to 90 micron. Temperature measuring range by using the camera is 8,000 to 22,000 is possible. Metal powder feeder is a dual hopper system, and powder preheating also possible. That will eliminate the heat affected zone on your existing or the base plate. So we have some feedback system also, smart optical monitoring system, we call that as SOMS. So that will also give you some feedback about the melting of things happening on the substrate side. This is actually the process flow which has happened in our laser DED machine. First thing is STL file input. So as I mentioned already, you have to make the CAD model, save in the STL file format. Then you send the file to the slicing software. What we are using is Cura. So we input the STL file, right? So what Cura will do is it will slice to the required thickness, right? Then once the slicing was happened, it will be converted into G code file. Then the G code file is imported to the ABB Robo Studio. Robo Studio is the proprietary ABB software, right? So ABB has the software called Robo Studio. So that will convert the conventional G code into the ABB robot program. So after the conversion happens, you have to transfer that file to the ABB robot controller, right? And you have to give some machine specifications in the laser software interface also. Like you have to mention the laser power, you have to mention the speed of the laser scanning. So these things you have to mention in the laser software interface. Then turn on the nozzle, turn on the powder feeder gas, let's do a printing, right? Check during print and stop machine when completed. So this is the process flow what we are following for printing the metal components by using laser DED. These are all some of the video which we have taken during the printing. This is the substrate, this is the motion system, and these tubes carries the powders. Few tubes are for cooling the cladding head, few tubes are for transferring the powder. So for optimizing the process parameter, we first do a single track analysis. We first lay a single track and we measure the bead geometry, we measure the hardness, and then finally we will come up with the optimized parameter by using some optimization technique. Then what we do is we do a printing of the final component, right? And if you want, you can do what do you call it as you can measure the mechanical property, right? So just I'm moving into the parameter, laser parameter. So if you increase or if you decrease the laser power, say for example, mostly 500 watts power is very sufficient for melting the stainless steel powder. So if you use low laser power, what will happen is there will be lack of fusion. So the thermal energy you pour into the powder is not sufficient to fuse it. So because of that, what will happen? You will have a weak bonding, you have a porous structure. But if you use a high laser power, what will happen? you will have excessive melting. Sometimes it may get vapor also. There will be more keyhole. There will be more dilution. There will be more rough surface finish. So you have to optimize. You have to use the optimized laser power. Second one is the scan speed. That is done by the robot. If you go with the high speed, what will happen? Insufficient melting. The powder will be there, but it won't melt properly because it is moving at a very fast way. The energy requirement for melting the powder will not be sufficient. Because of that, what will happen? You will have poor bonding. You will have underfill defects. Outer surface, you may see it is melted, but inside there will be powder form, right? And if you go with the low speed, what will happen? You will have more overheating, right? You are spending more time. You are giving more thermal energy to melt the powder. Because of that, what will happen? Large heat affected zone. You will have distortion. You will have coarse microstructures that leads to reduce the mechanical problem. So use a proper scan speed. Third one is powder feed rate. Powder feed rate normally we will mention in grams per minute. If you use a very low powder feed rate, you will have very under deposition, poor layer continuity, porosity. If you use high rate, unmelted powder will be there. Irregular bead geometry will be there. Surface roughness not that much good, right? The fourth main parameter is laser beam diameter. So as I have shown in the specification itself, you can change the laser diameter. If you go with a smaller diameter, you have high energy density because more energy is focused on a very smaller diameter. Finer resolution can be printed. But if you use larger diameter, what will happen is wider melt pool, lower resolution, right? These two are the drawback of going for larger spot diameter. So you have to optimistically select a spot dia, or you call it as laser beam layout. Next one is build orientation. This affects the quality of the part. So most of the time it will become anisotropy. Vertical, if you vertically build it, you have to place more supports. Optimized orientation improves load bearing strength and minimize distortion. So as said, in subtractive manufacturing, you should consider DF, design for manufacturability. And I have mentioned in the early stage itself, for additive manufacturing, you don't want to consider the DF, design for manufacturing. But for some extent, you have to think about that also. So that will give you better results, right? So you want to look for mechanical strength, then you consider the design also during the design stage itself, so that you can achieve 100% strength even in additive manufacturing. Next one is layer thickness. Thin layer, obviously you will have better surface finish but longer build time. Thick layer, you can build fastly, but high porosity, poor resolution will be there, but you can print the component in a very fast way, right? And finally, hatching pitch. So it is nothing but the distance between the successive layer, right? So in the horizontal plane. So if you have a small pitch, you will have more overlap. So dense product will be made. If you have large pitch, less overlap. Because of that, you will have lack of fusion, porosity, weak interact bonding, right? So these are all the parameters you need to consider. You need to optimize. You need to use it in your machine for the betterment of product quality. Okay. So advantage and disadvantage. Advantage, it can repair existing part. Ability to print functionally graded material. Ability to print very large structure. No waste powder to recycle. High printing speed. High material deposition rate. Multi-material capabilities also available. But drawback, DED does not create support structure, which limits the production of parts with overhangs. DED systems are typically very expensive. High cost of raw material. distortion, porosity, and inhomogeneity in the inhomogeneity in the printed component. And also it has high surface finish. So these are all the drawbacks or the limitations or setbacks in the DED, laser DED. So any doubt so far? Have any doubt in the laser DED mission? Or are you looking for some research statement? You can ask. So I will clarify, or I will give you some problem statement. Any doubt?
I don't know. Nobody is responding, sir. You can continue.
Yes, yes. 1 second, sir.
Hello, sir.
Yes, yes.
Sir, myself, I am Raghuram.
Yes, sir.
Yeah, I have a small doubt. I'm working on biomaterials.
Yes, sir.
So when I during the session, I have a doubt which arises.
Yes.
We are having some process parameters like laser, power feed rate, and
Okay.
scanning, etc. So during titanium-based biomedical implants producing, we are working on some titanium-based bio implant uh, production.
Okay.
That is, we are looking to some papers.
Okay, sir.
What are the most significant parameters that we have to consider when we are working on titanium-based biomedical implant producing?
Yes, sir. So I will tell you, sir, actually for making bio implants, the best suitable process is powder bed additive manufacturing.
Yes, sir.
The directed energy that you called as powder fed, FED, powder fed, that is what I have discussed.
Yes.
Normally in the powder fed DED, the drawback is the surface finish is not good that much. You will have high surface roughness value.
Yes.
So if you want to make bio implant, it is better to go with powder bed additive manufacturing that you called as SLM. Right?
Okay.
So that I didn't discuss, sir, in this lecture. But we have one machine in our campus. So that can have the capability to print bio implants. And of course, you have to consider all the parameters, sir, because this is more risk is involved. You have to consider the laser power, you have to consider the scan speed, you have to consider the inert atmosphere also. You have to tell about the inert flow rate also, inert gas flow rate. You have to consider the spot dia, right? So everything, every parameters are very important while printing bio implants, right?
Yes.
There are many research articles are available that will help you to select the proper process parameter, or you can do a single track analysis to find out the optimum process parameters to print the bio implants.
Okay.
So as of now, we didn't do any bio implant manufacturing in our campus.
Yes.
So we are working on the industrial applications. So we closely work with DRDO, we closely work with ARDB research panels. So we are making conformal cooling channels, but in the implant side, we didn't touch so far, sir.
Okay. So we have facing that challenge also. That's why I asked. When we are looking to make any bio implant, that is metal-based dental implant, metal-based implants.
Yes, sir.
So facilities very limited.
Yes, we have machines, sir. Maybe because that machine is not in my control. We have a metallurgy department. They have the SLM machine. Maybe you can approach them. Maybe they may help you to print bio implants. Or else you can approach IIT Palakkad or IIT Chennai for printing the bio implant. They have the good facility for making bio implants.
Yeah, IIT Palakkad, we approached Mr. Kanmani Subbu sir.
Kanmani Subbu sir, yes. And Afsal
Okay.
Ahmad, K7, they are having this facility. So you can approach them for printing components.
Okay.
But for DED, we have a good facility. You can approach anytime. So we are ready to help you.
Sure. Thank you. Thank you.
Yes. So anything else? Shall I continue?
Yes, sir, you can continue.
Yes. So the next method is wire arc additive manufacturing. This is also belongs to the DED family. But the major difference is two things. One is, as I already mentioned, the feedstock material will be in the wire form. Feedstock material will be in the wire form. This my screen is visible. Hope my screen is visible. So it uses an electric arc. So the thermal energy is got from using the electric arc. So it uses an electric arc to melt metal wire, which is deposited layer by layer to build parts. So wire arc additive manufacturing is efficient, called as versatile, and well suited for creating complex structures. WARM, shortly called as WARM, wire arc additive manufacturing, can produce deposition rate unimaginable. It is up to 10x greater or potentially even higher than the other additive manufacturing technique. So that is the greatest advantage why people are preferring. So you can make products in a very fast way if you use wire arc additive manufacturing, right? I will show you the machine which what we have. So we have Fanuc ArcMet 100 IC robo. It's a 6-axis robo. Along with the 6-axis robo, we have a 2-axis positioner. So totally an 8-axis robotic system is available. And by using the MIG welding power source, we use Fronius power source. In the Fronius power source, we have the beautiful technology called cold metal transfer technology. So by using that, we are making 3D printing of components, right? So far we tried with several materials, all aluminum alloy grades, all stainless steel, super alloys, cobalt based alloys. So we tried with several materials, and many customers are regularly coming and printing component by using this machine. The maximum reach is 1420 mm. So even you can print component for a size of 700 to 800 mm plus 800 mm plus 800 mm is possible by using this machine. And this is the controller photo of the Fanuc robo. So you have a cycle stop button, mode switch selection for teaching and for auto, and you have interface panel to feed the program to the controller. And this is your teach pendant that will help you to program your robo, right? So when we talk about the application part of wire arc additive manufacturing, start with automotive industry, construction, structural fabrication. See, this is the bridge which is in Netherlands. So it is completely built by using wire arc additive manufacturing. And this is the impeller, this is the blade, which is propeller shaft. This is completely made by wire arc additive manufacturing, right? So the important process parameter in the wire arc additive manufacturing is welding current. The welding current, if it is very high, sometimes some people will use 80 amps or 130 amps or 140 amps. So if it is very high, then what will happen is you will have deeper penetration, larger multiple formation, faster deposition, but risk of high dilution and coarse grain, even more heat affected zone. But if you go with a lower current, what will happen? You will have lack of fusion, poor bonding and porosity formation. And the voltage, if you use high voltage, you will have wider arc. If you use low voltage, you will have unstable arc. So you have to maintain a proper voltage, right? And the wire feed rate Wire feed rate will be, you will mention in sometimes grams per minute also, sometimes meter per minute also. This depends, right? So here the wire feed rate, if it is very high, then the more material will be deposited, larger bead formation. If it is low wire feed rate, underfill and discontinuous layer or thin bead formation. And the next one is a travel speed. So this you can relate with the laser DEDS scan speed. So if you have high speed, bead formation will be narrow. If it is low speed, wide bead formation. And if it is a low speed, you will have excessive heat input. So that will lead to distortion and rough surface finish. If it is high speed, lack of bonding and poor surface finish is possible, right? And you have to maintain the shielding gas flow rate properly. You have to wisely select the wire diameter. In market, 0.8 mm, 1 mm, 1.2 mm wires are commonly available. By using that wires only, you can print components. And layer thickness. So you can have a small step over, or you can have a large step over. Large step over problem is you will have very uneven surface. Small step over, or you have less uneven surface. And build orientation is also very important for printing the component. So this is a hybrid additive approach that we will discuss later. Before that, we will have a fair comparison between powder bed, powder fit, and wire arc additive manufacturing. Why I have compared these three is, these three are very famous in metal additive manufacturing industry, right? Start with the feedstock material. The powder typically in the powder bed machine is 20 to 40 micron, whereas the DED, powder fed DED, is 45 to 90 microns. Whereas in the wire arc additive manufacturing, 1 mm or even you can go up to 1.2 mm also, that is possible. When we talk about the heat source, laser is the heat source. Powder fed also, laser is the heat source, right? And in the wire arc additive, electric arc is the heat source. And heat source cost is very high in the powder bed, moderate in the powder fed, and very low in the wire arc additive manufacturing. And this is another very important thing, deposition rate. Deposition rate in powder bed will be around 0.1 to 0.2 kg per hour, right? Whereas in the powder fed machine, it will go up to 2.27 kilogram per hour. And in the wire arc additive manufacturing, it may go up to 14 kg per hour. You just imagine. So how fast the material is deposited. So faster deposition, finally faster the component maybe comes out from the manufacturing machine, right? But normally the build size is very the smaller in the powder bed machine because of the cost of the machine, right? Because it is done in a closed environment. In the powder fed machine, comparatively it is higher, and in the wire arc additive manufacturing, it is comparatively largest than other two techniques. So accuracy aspect, powder bed machine stands first, second with powder fit, and finally with the wire arc additive manufacturing. And the surface finish also very good in powder bed, moderate in powder fit, and poor in wire arc additive manufacturing. So scan speed, this and all, some fair comparisons, right? And when we talk about the wire arc additive manufacturing, we have a unique facility. So we have a Fronius machine which is interfaced with the AB Fanuc robo, which is interfaced with the Fronius power source, and we have a ABB robo which is interfaced with the EWM power source, TIG welding power source, and we have a gantry welding machine. This will help you to do a cladding. We have two torches, one is for MIG welding, another one is for TIG welding, right? And we have 5-axis tall robo, which will help you to do a MIG welding. And we have a 6-axis collaborative robo from the company called Universal Robots, which will help you to do a MIG welding. And we have a turbo TIG welding machine also available in our center. And this is another beautiful facility that we called as a laser powder PED. So this photo you have seen already in the previous slides. And this is another development for the cladding purpose. So even by using this cladding machine also, you can print components, right? And this is another robo which is interfaced with the MIG welding power source, metal and gas power source. And we are also offering industrial robot programming course. We are actually a FANUC authorized training center. We offer course for students, we offer course for researchers, we offer course for industry people to tell how to do a robo programming, how to operate the robo, how to maintain the robo. So in these three aspects, we are conducting regular program for the outsiders, right? So that's all about the additive manufacturing core concept and future trends. So now the session is open for questions. So if you have any doubts, maybe you can pitch in now. Any doubts from the audience? If interested, even I can share you some aspects of hybrid additive manufacturing also, if you are interested. Or else maybe we can wind up the session.
So audience, if you have any doubt, you can ask now.
Any doubt from the audience side? Umanath sir?
Yes, sir.
I think there is no questions from the audience side, sir.
Yes, sir.
Can we wind up or?
Yeah, we can wind up, sir.
You
No
have
issues.
any queries? Yes, sir. Yes, sir. Yes, sir. Right.
We can wind.
What are the different process parameter optimization technique adopted? Sir, one question from the chat box. What are all the different process parameter optimization technique? There are several methods are available, sir. To start from Takuchi, ANN. So there are different methods. So particle swarm optimization, anything you can use it, sir. So mostly research scholars are using Takuchi method. Some people are using a neural network method. Some people are using some machine learning techniques to optimize the process parameter. Right? It depends upon the user. Right? Every technique there has pros and cons. Any other questions?
And Raghurat sir, from one side, yesterday also someone was telling one of my colleague also used box Bacon method, response surface methodology for this optimization.
Yes, sir. Correct. So even one of my scholar is using the RSM method, box Bacon method, for optimizing the process parameter.
Yes. Sir, I think so.
Yes,
that's it. If
yes,
if they have any doubt now, I will give them your number of mail ID. They can contact you.
Yes. Thank you.
Sure.
Thank you, sir. Thank you.
So on behalf of Sripati Institute of Management Technology, I thank Prabhakaran sir for delivering the session. I'll share the feedback form here and in the group also. And in case if you have any doubt, you can contact Prabhakaran sir. I'll give you the contact details. So with that, we'll end up this session now. The afternoon session will begin at 2 o'clock. Please join by 1:50. Thank you.
Thank you, sir. Thank you.